The topic is scalar magnetic potential. As in electrostatic, we can use a relationship between electric field intensity E and electric potential, and the relationship is E vector is equals to minus del V. Means the gradient of a potential is equals to minus E vector. So, as in electrostatic, we have a relationship E vector equals to minus del V. We can write relationship between magnetic field intensity H vector and magnetic potential V suffix M. Here V suffix M is a scalar magnetic potential. So in magnetostatics, the H vector is equals to minus del V suffix M. Now, as we know that the curl of E is equals to 0. That is, in electrostatic, the curl of electric field intensity E is equals to 0 because electric field intensity is conservative in nature. But in magnetostatics, there is an Amperes law which defines that the curl of magnetic field intensity H is equals to current density J vector. So here we use a Amperes law, that is curl of H equals to J vector. And here we use an identity, that is curl of gradient of potential is equals to 0. Which means that when we find a curl of a gradient of a potential, we get a 0. Means there is no curl of gradient of potential. And the second identity is the divergence of curl of a vector A vector is equals to 0. So for scalar magnetic potential, we use these identities. And using Amperes law, we use curl of H equals to J vector. Now, in place of H vector, we can write minus gradient of V suffix M. And here we get a identity, that is curl of gradient of a potential V suffix M, and its value is 0 by using an identity, that is curl of gradient of potential equals to 0. Here minus is taken outside, then we get identity, that is curl of gradient of a potential V suffix M is 0. So we can say that the curl of H vector equals to 0, but in magnetostatic, the relationship of Amperes law is curl of H equals to J vector. So here there is a point, the magnetic scalar potential V suffix M is only defined in the region where current density J vector is equals to 0. Means a region where there is no current density, in that region we can determine the scalar magnetic potential V suffix M by using an identity and Amperes law. So here we conclude that the magnetic field intensity H vector having a relation with the scalar magnetic potential V suffix M by H vector is equals to minus gradient of Vm. This is possible only when the current density is equals to 0. Now, the next point which is to be noted, the scalar potential. The scalar potential is V suffix M. The scalar potential satisfies the Laplace equation. Here the Laplace equation in electrostatic is del square V equals to 0. Similarly, the Laplace equation in magnetostatic is del square V suffix M equals to 0. And this happens only when the current density J vector is equals to 0, because the scalar magnetic potential exists where the current density J vector is equals to 0. Now, as we know that the divergence of magnetic flux density B is 0 because there is non-existence of the magnetic monopole, means there is no isolated magnetic charge. The magnetic field lines are always continuous. There is no source point or end point. It is a closed one. So here the divergence of magnetic flux density B vector is equals to 0 and it is a fourth Maxwell's equation. So here we use this, that is divergence of B vector equals to 0, and in place of B vector we can write mu naught H vector. Here mu naught is called permeability of free space and it is a constant, so it taken outside. So we get divergence of H vector equals to 0. Now in place of H vector we can write minus gradient of Vn. So here we get del square V suffix m equals to 0 by taking mu naught to the right side, that becomes 0. So we get a Laplace equation, that is del square V suffix m equals to 0, and in this way we can find that the scalar potential V suffix m satisfies the Laplace equation, and it is only for region where current density J vector is equals to 0. Now the scalar magnetic potential can be directly defined by line integration S dot dl with minus sign, just like a potential in electrostatic, that is V equals to minus integration E dot dl. So the scalar magnetic potential can be defined as minus integration S dot dl and its unit is ampere because the unit of magnetic field intensity H is ampere per meter and dl vector having unit meter. So we get a ampere, that is the unit of scalar magnetic potential. So here we introduce a scalar magnetic potential and its unit is amperes, and the scalar magnetic potential is only defined in that region where the current density is equals to 0. Next is vector magnetic potential. What is the requirement of vector magnetic potential? Because in Amperes law we know that curl of H vector equals to J vector, and in case of scalar magnetic potential we use J vector equals to 0, means we use a current density 0. So when there is a current density exists, there is a vector magnetic potential. So the vector magnetic potential exists where current density J vector is present. When current density J vector is 0, in that region there is a scalar magnetic potential, and when the region having a current density J vector, then we talk about vector magnetic potential. So magnetic vector potential is defined in such a way that its curl gives the magnetic flux density. So here the magnetic vector potential is defined in terms of magnetic flux density, and for magnetic vector potential when we take its curl then we get a magnetic flux density. So here a relation that the curl of a magnetic vector potential A vector is equals to magnetic flux density B vector. So the vector magnetic potential is denoted by A vector and its unit is Weber per meter. and it is defined by taking a curl of a magnetic vector potential, and it gives a magnetic flux density. And here we use an operation that is curl. We cannot use a divergence here because by using curl, and we know that the curl of a vector gives vector quantity. So we use here curl operation, because in using divergence of a vector, the divergence of a vector is a scalar quantity. So we use curl operation. The curl of a vector magnetic potential gives a magnetic flux density B vector. So B vector equals to curl of A vector. Here A vector is called vector magnetic potential. Now we use the Amperes circuit law, that is curl of H equals to J vector, and the magnetic flux density B vector equals to mu naught H vector. That is in a free space. Now from here, H vector is equals to B vector upon mu naught. So in place of H vector of the Amperes circuit law, we write B vector upon mu naught. So here we get a curl of B vector equals to mu naught into J vector. Here we take mu naught to the right side. So we get curl of B vector equals to mu naught into J vector. Here we take a free space. That's why we use mu naught. So the Amperes circuit law in terms of magnetic flux density B vector is written as curl of B vector equals to mu naught into J vector. Now, from the definition of magnetic vector potential, that is, the curl of a magnetic vector potential gives a magnetic flux density B. Now here, as the Amperes circuit law is curl of B vector equals to mu naught into J vector, similarly, we take a curl of vector B for magnetic vector potential. So the left side is curl of vector B and the right side becomes curl of vector A, that is curl of magnetic vector potential A vector, and this is equals to mu naught J vector after equating both equations. So the curl of B vector equals to curl of A vector, and that is equals to mu naught J vector. So from here, the curl of A vector is given by using the Laplacian of a vector. So from the definition of Laplacian of a vector, the Laplacian of a vector, that is del square E vector, is equals to gradient of divergence of a vector A minus curl of A vector. So this is the definition of Laplacian of a vector, that is del square A vector is equals to gradient of divergence of vector A minus curl of vector A. Okay, so from here we use a curl of A vector. Curl of A vector is equals to gradient of divergence of A vector minus del square E vector, and it is equals to mu naught J vector. And we know that the gradient of divergence of a vector is equals to 0. This is because in magnetostatic we use a DC current only. That's why the divergence of a vector A equals to 0, because the magnetic flux lines or magnetic field is continuous. It has no divergence. So the vector magnetic potential also having no divergence. So in this way we can get a equation that is minus del square E vector equals to mu naught J vector. So from here we get a Poisson's equation, that is vector Poisson's equation, and it is del square E vector equals to minus mu naught J vector. So this is a vector Poisson's equation in magnetostatics. So here we use a Poisson's equation, that is del square E vector equals to minus mu naught J vector. In case of scalar magnetic potential, we get a Laplace equation, that is del square V suffix m equals to 0. And in case of vector magnetic potential, we get a Poisson's equation, that is del square A vector equals to minus mu naught J vector. So here we use a vector Poisson's equation in Cartesian coordinate system, that is XYZ. So the vector magnetic potential in Cartesian coordinate system is written as Ax unit vector x plus Ay unit vector y plus Az unit vector z. Similarly, J vector in Cartesian is written as Jx unit vector x plus Jy unit vector y plus Jz unit vector z. Now after equating left side and right side, we get a three equations, that is del square Ax equals to minus mu naught Jx, del square Ay equals to minus mu naught Jy, del square Az equals to minus mu naught Jx. So these are the three Poisson's equations in magnetostatics. In case of electrostatics, the Poisson's equation is given as del square V equals to minus rho V upon epsilon naught. So this is a Poisson's equation in case of electrostatics. And the Poisson's equation in magnetostatic is del square A vector equals to minus mu naught J vector. Now, in case of electrostatic, the Poisson's equation is del square V equals to minus rho V upon epsilon naught. And in case of electrostatic, the electric potential V equals to Q upon 4 pi epsilon naught R. And in terms of volume charge density rho V, we can write Q equals to volume integration rho V into dV. So the electric potential V is equals to 1 upon 4 pi epsilon naught volume integration rho V dV upon R. Now here we consider that minus rho V upon epsilon naught is equals to del square V. In Poisson's equation of electrostatic, we have a ratio that is rho V upon epsilon naught, and it is equals to del square V. So here we take a relationship from electrostatic and apply on magnetostatics. So from here, the electric potential is equals to rho V upon epsilon naught. We take a outside the bracket, that is rho V upon epsilon naught, because this term is related to Poisson's equation in electrostatics. So rho V upon epsilon naught is taken outside the bracket, and within the bracket we have 1 upon 4 pi volume integration dV upon R. So here we take a relationship of Poisson's equation with electric potential and we apply on magnetostatics. So in magnetostatics, the Poisson's equation is del square Ax equals to minus mu naught Jx. And here in electrostatics, the right side is minus rho V upon epsilon naught. And in magnetostatic, the right side is minus mu naught Jx. And within bracket, we have a term that is 1 upon 4 pi volume integration dV upon R. So from taking the relationship of Poisson's equation and electric potential, in case of electrostatic, we can define the magnetic potential, that is Ax equals to mu naught Jx within bracket 1 upon 4 pi volume integration dV upon R. So we take it combinedly, that is mu naught upon 4 pi volume integration Jx upon R into dV. So this is a vector magnetic potential in terms of current density J, and this is a formula that is a magnitude one. Similarly, Ay equals to mu naught upon 4 pi volume integration Jy upon R into dV, and Az equals to mu naught upon 4 pi volume integration Jz upon R into dV. So in general, we can write a vector magnetic potential A vector equals to mu naught upon 4 pi volume integration J vector upon R into dV. So this is a vector magnetic potential in terms of current density J vector, that is mu naught upon 4 pi volume integration J vector upon R into dV. And here we use a relation, that is B vector. Magnetic flux density is obtained by taking a curl of a vector magnetic potential. that is B vector equals to curl of A vector. And this will happen when we take divergence of B vector equals to 0. So that the divergence of A vector is also equals to 0, because we know that the divergence of curl of a vector equals to 0. So this is a general formula in terms of current density. We can also define the vector magnetic potential in terms of current configuration. That is, in magnetostatic there are three current elements, that is ideal vector, that is a current element which define a differential length that is equals to k vector into ds. Here k vector is called surface current density. That is in the case of sheet which carries a current and having a surface current density k vector. It is also equals to j vector into dv. In all the three current elements, that is ideal, kds and jdv, having a unit that is ampere meter. Because in a first element, that is ideal, I having a unit ampere and dl vector having a unit that is ampere. So the first term having a unit that is ampere meter. The second current element is k vector into ds. Here k vector is equals to I upon b. B is a perpendicular distance. So the unit of k vector is ampere per meter. And the unit of ds is a differential surface, that is meter square. So we get a unit of k vector into ds is ampere meter. Similarly, the j vector is current upon area, that is ampere per meter square, and dv having a meter cube. So j vector into dv having a unit that is ampere meter. So in all the three standard current configuration, we have a unit that is ampere meter. So in place of j into dv, that is j vector into dv, we can replace by ideal vector and k vector into ds. So we get a vector magnetic potential for volume current, that is mu naught upon 4 pi volume integration j vector dv upon r. This is for volume current. For surface current, we use a surface current density, that is k vector into ds. So the formula is mu naught upon 4 pi surface integration k vector ds upon r. And for line current, we use a ideal vector, that is the formula of vector magnetic potential is mu naught upon 4 pi line integration ideal vector upon r. This is for line current. So in this way, we can find the vector magnetic potential, and the vector magnetic potential exists where the current density j vector is present. So this is the difference between scalar magnetic potential and vector magnetic potential. Now we can represent a magnetic flux in terms of surface integration b dot ds, and the vector b in terms of vector magnetic potential is written as surface integration curl of vector a dot ds vector. And we know that the surface integration of curl of vector a dot ds is equals to closed line integration a dot ds. That is the Stokes theorem. The Stokes theorem is a relationship of a closed path defines some open surface. So here, by using a Stokes theorem, we get a magnetic flux, that is closed line integration a dot dl is equals to surface integration b dot ds. So in this way, we define a potential in magnetostatics, that is, first is scalar magnetic potential, that is written as V suffix m and its unit is ampere, and second is vector magnetic potential. It is denoted by A vector and its unit is Weber per meter. Because here we take a magnetic flux, that is closed line integration A dot dl. So in terms of A vector, we get d psi upon dl vector.